stopped. It's actually off by like 10 minutes. Oh, it stopped. Yes, it has stopped. Ooh. Do you ever see what happens with a battery when it goes past its expiry date? You know, the batteries have expiry dates on them. So they start to leak. You see? Have you ever seen that before? Yeah. You seen that before? So someone's kept this battery in too long and now it's stuck in there. Okie dokie. One more minute and then we'll start the next lesson. It would be wonderful if you got those 4 questions finished. You're nearly finished, aren't you? Good job. And C, Bill? Wonderful. And you're on 4 as well, or are you C4? Yeah, okay. How many? Okay. Good job. You're not completely brain dead from your lack of sleep then. You've got some power left in you. Okay, 1 minute. 1 minute and then we'll continue. Do you think you can get it, Matt? Don't worry about part D. I don't know why I made it so hard. I'm just looking at what I wrote. If you could get to 4C, that's enough. All right, we'll continue now. Like I said, this is an easy lesson compared to what you just did previously. All right, you can write that down. Transformers. You got that? Okay. Got that on deck? Right. So, in this lecture we'll study transformers. So here's an example of a transformer. This one is Optimus Prime. You know this, of course, don't you? Yes. Yeah. Who does he fight? Megatron. Leader of the... Is that correct? Very good. And Optimus Prime is leader of the Autobots. Very good. Okay. So, no. Okay. Sorry. This is a transformer. It's not as exciting as the other transformers. So, what exactly is a transformer? It's actually a very, very simple machine. Now, it's maybe hard for you to see this. I'll have to explain a little bit here. So, what you have is a piece of iron. And then wrapped around this side is an input voltage. So there's a current here. And by the way, this is AC. This current is alternating back and forth. Okay? And then wrapped around this side is a secondary wire. And it's important that the number of turns here is different to the number of turns here. Now, this is what happens. Your charge moves along here, but then it's an alternate current, so the charge moves backwards. Okay? Now, you remember from Fleming's right-hand rule Do you remember when you have a current that's moving, you have a magnetic field around it? Okay? So, can you picture as this current moves in, there's a magnetic field around it. Now, what happens when the current switches direction is the magnetic field switches direction. So here you have a magnetic field that keeps changing. What did Faraday say? Faraday said that when you have a change in magnetic field, what happens? Do you remember? Remember if you have a delta B, what happens? What can you make? No? So remember, Faraday's law of induction says if you have a change in magnetic field, then you get a voltage. So what happens here is there's a magnetic field that's made by this current, and this magnetic field that comes out of here actually causes a current to appear in this wire. But what's interesting is the current that appears in this wire, because of this wire, it will have a different voltage than what was in this one. Okay. Now, before we calculate what the voltage will be, I need you to draw this. Let me just, if you can't see the words, let me just read them to you. So this one here is called the primary current and the primary voltage. And this one here is called the secondary current and the secondary voltage. And this is the magnetic flux. This is the transformer. And I think you can try and draw that. Okay, you drew that? Yeah? By the way, if you can see in the picture, the current is coming to the right here, and the induced current is moving to the left. There's actually a law. You remember which law? Remember? Lenz's law. Remember Lenz's law? You don't remember Lenz's law? Okay. Lenz's law says the induced current flows opposite to the... You're looking for it there, Matt? Did you find it? Yeah. Alright, let's continue. Let's calculate a formula. Okay, so look. Here's our piece of iron. And this is wrapped around, and we'll say it has voltage V1 and N1 number of turns. And here, it's wrapped around, not as many times maybe, and it'll have voltage V2 and N2 number of turns. And we want to calculate what the new voltage will be. Okay, so first things first, this will make a magnetic field. And this magnetic field keeps changing its direction because the current keeps switching back and forth. So it means the magnetic field keeps switching around. So remember, Faraday said you'll get a voltage over here, and that voltage will equal the change in the flux over the time. Yeah? That's okay? Now, it actually, because this one has a current here as well, you can actually look at it from the other point of view as well, and you can get something similar here. The only thing that's missing in my formula is because this is turned n times, and 2 times, do you remember the formula we said total flux is NBA? So here this is equal to change in NBA over T. And this one here is also change in NBA over T. Whereas this is, you can't quite see it, but that's N1 and this one is N2. Okay? So here you can take the N out. That would be N2 change in BA over T, and this one here, V1 equals, oh sorry, I wrote N2, I meant N1, sorry. And this one here is N2 change in BA over T. Which is changing here, the B or the A? If you look at this magnetic field, which is changing? Is it the B or is it the A? What do you think? It's the B, because the area here is staying the same. Okay, so you could also take it out like this: V1 equals N2 times A change in B over time, and this one V2 equals N1 A change in B over T. What I'm going to do is just bring the N2 down here and bring the N1 down here. Uh-oh, I made a mistake with my N's, I'm sorry. That should have been a 2. What? That should have been a 1. Anyways, it doesn't matter because you don't need the proof. This V1 over N1 equals this, and this one here, V2 over N2 equals the same thing. So you can say those two are the same. So you get V1 over N1 equals V2 over N2. Or finally, you get V1 over V2 equals N1 over N2. I'm very sorry that proof was so messy. You don't need the proof, don't worry about it. So this is the formula I wanted to get to, which I probably have on the next page. So a transformer is a device that converts voltage, and the formula, the formula is here. Let me write that down a bit neater. That's the formula for calculating the voltage.
So what's the difference in transformer?
Oh, well, I'll put the slide up in a moment. You got that formula? Yeah. You don't need all of this. So I just need the first sentence and the last sentence. So the first sentence: a transformer is a device that transfers electrical energy between two circuits. Commonly, they're used to increase or decrease voltage. You got that? Just the first and the last sentence, okay? You have that, Matt? Yeah?
Yeah.
Does anybody remember from the electricity chapter the name of the device that decreases voltage? The circuit that we saw that decreases voltage. What is it?
Resistor.
No, yeah, that's true. Resistor does decrease voltage, and there's a special circuit that lets you control how much voltage you want. Do you remember? It was at the end of the chapter. Remember? That's also true. Not quite what I was looking for, though. Potential divider. Remember, the potential divider is a way to reduce the voltage. Now, what's interesting and useful about the transformer is you can use the transformer to increase or decrease voltage, which makes it more useful. So there's two types of transformer. The first one's called a step-up transformer. Guess what that does to the voltage?
Increases.
Yeah. And what do you think the other one is called?
Step down.
And what does it do? It decreases it. Okay. Now, I think it's good if you write this vocabulary down. So you could just write step up increases and step down decreases. Now, a lot of you have these transformers and you don't perhaps fully realize that you do. So do you see here on my laptop, this box here? This is a transformer. So inside of it is the iron, and on one side there's probably 220 loops in the primary, and in the secondary there's probably about 10 loops. And this is used to reduce the voltage from 220 down to 10 or whatever it is. So I think nowadays, like with the smartphones, the plugs are quite small, but at least the older phones, I don't know if you remember them, the plugs were quite big. Do you remember these? Like really big black plugs for old phones. You remember these?
Yeah.
Do you see that? No. Matt? Yeah. And they used to get quite warm as well, just like how this gets quite warm. That was the transformer for changing the voltage. Now, I don't know how the new phones do it, but I feel like they don't use this because it's too big. You know, because your phone chargers now, they just look like normal plugs, right? Like they just look like a normal plug, but not the older ones. Anyways, transformers you can use to increase or decrease voltage. Most household appliances need to decrease voltage. Yeah? Phones, laptops, and so on. Okay. So we already got the formula here, and you have the formula here. This only works if the transformer is 100% efficient, but it's not actually 100% efficient because you can put your hand on this and you can feel some heat. So it's not 100% efficient. If it is 100% efficient, we have this formula here. Again, if it's 100% efficient, the power that goes in, so here, if you look, the power that goes into this side must equal the power that comes out this side. What's the formula for power? Power equals IV. Yeah? If my voltage decreases, then what happened to my current? What do you think happened to the current? And remember, the power in must equal the power out. Increases. Why? Because. Power equals IV. And if this power has to stay the same, then if you drop the voltage, then the current must increase to keep the total power the same. Okay? So you have power in equals power out. So I can combine these two formulas. Let's do that. V1 over V2 equals N1 over N2. P1 equals P2. So that means I1 V1 equals I2 V2. Yes? V1 over V2, what does that equal? I2 over I1. Can you see that? V1 over V2 equals I2 over I1. I can put these together and I can get N1 over N2 equals V1 over V2, which equals I2 over I1. So I can have this formula for current. It's the opposite way around than for voltage, okay? So you can get this formula as well. Alright, you need these three formulas, and please make note that they only work if it's 100% efficient. Got that? Continue? Andek?
Yeah.
Yeah?
Yeah.
Let's have a look at an example. So, you have a small toy. The toy only needs 6 volts, and the power supply is 220 volts. The number of turns on the primary coil is 4,400. How many turns are on the secondary coil? So, is that N1 or N2? What do you think? N1, because it's the primary coil. The 6V? V2, because it's the voltage you want at the end. At the end. And the 220 is the power supply, so that's the V1. Yes? Can you give me the N2? See what you get for N2.
Okay.
120 sounds reasonable to me. Wait, 120? Oh yeah, okay, sorry. 120 sounds reasonable to me. So the formula is V1 over V2 equals N1 over N2. And I want the N2 here. So N2 is 6 over 220 times 4400, which is 120. Was it? No, yeah. Isn't it? Yeah. Is that okay? So, I mean, this lesson is not too difficult. It's just using simple enough formulas. That's all the example I wanted to do. In the exam, this is a common enough question in section A, and it's kind of a nice question because it's not too difficult. Yeah. I tell you what time are we at? Okay, I'll let you leave after 10 minutes. I'll let you leave a little bit early since you look so exhausted. So can you just try these for 10 minutes? You might even get them all finished, then you can go off, okay? Then you can go to bed nice and early tonight. Do we have class tomorrow?
No.
No, okay.
You have to repeat tomorrow?
Do you have 9 o'clock class tomorrow?
No. We'll be at 7:30. You have
At
to
9 o'clock?
No, 10.
You get a little bit of a sleep then.
Are we setting our experiments tomorrow? What is it? For
Yeah, I think what we'll do, I think what I was going to do is, not, in our next physics class, we'll start the experiments. What I'll do is, I have to prepare you for what you're going to do. I know that sounds dramatic. So I want to demonstrate what is involved, and then maybe next week we can do I'll let you do the experiments, and then after that week, we can talk about what we need to do to write the report. Okay, so I think once Kim and Chow are here, we'll talk about the experiments in the next class then. Okay.